Thank you. Okay.
Hi guys, this is my video. I read A Brief History of Time, and this will be my summary, a brief summary of A Brief History of Time. So, starts off. Oh no, is this too fast? Let me slow it down for you. A Brief History of Time is a book written by Stephen Hawking, and it was published on April Fool's Day, 1988. It mainly focuses on physics, which is not easy to understand. However, Hawking set up the book in a way that makes it quite easy to understand with only basic knowledge. The first thing that he talks about is our view of the universe and how it has changed through time. We used to think that we were the center of everything. We were the center of the universe. However, through observation, we learned that we weren't even the center of our solar system. We were completely wrong. Then the book talks about the relationship between space and time and general relativity. This law states that nothing with mass can travel at or over the speed of light. This is because to increase the speed of something with mass over the speed of light, it would require infinite energy, and you just can't do that. The next chapter states that we live in an expanding universe. However, it might be expanding slow enough that gravity will take over and time will end in a big crunch. The subsequent chapters deal with tiny particles and the natural forces. There are 4 of these forces: gravity, the strong force, the weak force, and electrostatic attraction. When one deals with super small particles, there's also something called uncertainty. This is because when you have a small particle and one shoots light at it, to be able to see it, the velocity or position of it will change, and the more accurate you know one, the less accurate you will know the other. Chapter 6 is called Black Holes, and Chapter 7 is called Black Holes Ain't So Black. Basically, a star is hot because of gravity. It forces the hydrogen particles within it to move really fast and bump into each other, which creates heat. This heat holds off the gravity and it gives the star its shape and size. Eventually, all of the hydrogen and sometimes helium fuel is burned off, and if the star is big enough, the gravity will be so strong that the star will actually shrink into a point called a singularity. This singularity will have a gravitational force so strong that nothing, not even light, can escape. However, this has a problem because of something called the law of conservation of mass. Matter cannot be created nor destroyed. So then what happens to the matter when something falls into a black hole? Well, this is why black holes ain't so black. The event horizon of a black hole is the edge. Nothing inside of that line can go out, but everything can fall in. When something falls into a black hole, there are these things called virtual particles around the event horizon. When something falls in, they split into 2. They split into a real particle and an antiparticle. It really doesn't matter which one falls in and which one leaves, but what matters is that one appears to leave from the very edge of the event horizon. This is what we call Hawking radiation. Then, the book talks about why we experience time passing by and why it does not run backwards. It also suggests the possibilities of traveling through time and the mathematical plausibility of it. Finally, Stephen writes about string theory. This is a new way of thinking that may actually give us a way to create a unified theory of physics connecting everything we know about the universe. However, the book verges on philosophical as there are many questions left unanswered. Some of the questions that one can wonder about from this book are: how close are we to finding the smallest building blocks? Are we almost there, or can it get a lot smaller? Are we almost done finding new laws and can make a unified theory? Stephen thought we might be close, but he wasn't sure. Will we ever be able to detect a black hole directly, and will our depictions of them be correct? And what will it actually take to travel through time? Will it take a lot of energy or just a clever machine? The answer to the third question is that we have in fact been able to see a black hole, just recently. The results are quite surprising, but let's talk about the image. It took a worldwide network of telescopes to be able to capture this image, and it took 2 years to render so that we can be able to see and actually visualize what a real black hole looks like. This is astounding because a year ago there was a visualized illustration that looks almost exactly like the picture that we took. This is great news. It means that our predictions are probably correct, which implies that general relativity, which states that time ends in a black hole, could be true. This is amazing. Hopefully, we will be able to learn more about our universe with this image. Thank you for watching.